Welcome to the deep dive. Today, we are tackling, well, a pretty huge subject, astrophysical black holes. We've got a whole range of sources here, covering observations, the physics, how they interact, basically the whole spectrum. Our mission, to try and synthesize the core ideas about these things, from the smallest stellar ones to the supermassive giants.
Yeah, it's a great topic for this kind of dive because, despite the enormous differences in scale, we're talking mass differences of billions, the fundamental physics driving them is remarkably consistent. It really boils down to just a few key things.
Okay, what are those key things then?
Well, mostly it's the black hole's mass, obviously. Then how fast it's spinning, that's the spin parameter, JL dollars. Also, how much material it's actually eating, its fueling rate, which we call DMNL. And maybe the most surprising one is simply the angle you happen to be viewing it from.
The viewing angle. Okay, we'll definitely need to unpack that, but let's start with the mass. You said the physics is unified, but the sizes are all over the place. What are the main categories?
Right, three main classes. We can start small with the stellar mass black holes.
Okay, the little guys, relatively speaking.
Ha, exactly. Relatively. These are what's left after a really massive star dies. You often find them in binary systems, orbiting a normal star. We call those black hole X-ray binaries. Sometimes when they're actively feeding and launching jets, we call them microquasars.
And how do we know for sure it's a black hole and not, say, a neutron star? Is there a specific mass cutoff?
There is. It comes down to what we call the mass function, which we calculate from the binary orbit. If that calculation shows the compact object's mass is more than about 3 times the mass of our sun, $3 in both.
Then it's just too heavy to be a neutron star. Gravity wins. It has to be a black hole.
Okay, so 3 solar masses is the limit there, but how do they form? You said massive stars, but I remember reading something slightly counterintuitive about the final mass.
You're right. It is a bit tricky. You need a star that starts its life bigger than around 21 solar masses to even have a chance of collapsing into a black hole.
But, and here's the catch, those really massive stars, especially in galaxies like ours today, have incredibly strong stellar winds. They blow off huge amounts of their own mass over their lifetimes.
Ah, so they shed weight before they even collapse.
Exactly. So much weight, in fact, that the final remnant, the black hole itself, almost never seems to end up heavier than about 10 solar masses. Those winds are like a cosmic regulator, at least for now.
Interesting. Okay, so that's the stellar mass range. Now let's jump way up the scale to the giant.
Right, the supermassive black holes, or macroquasars if they're active. These are the absolute monsters residing in the centers of most, maybe all, large galaxies.
Their masses are just staggering.
Oh, yeah. We're talking millions to billions of times the mass of the sun. The range is roughly 106 to S up to maybe even 10. These are the gravitational anchors of galaxies.
How do we even measure something that massive and that far away?
Well, for our own Milky Way, we've actually tracked individual stars orbiting the galactic center for decades. They whip around an invisible point of void at incredible speeds. Those orbits let us nail down the mass of our central black hole very precisely. It's about 4.1 million solar masses, plus or minus maybe 500,000.
Wow. Direct observation.
Direct observation of the effects, yeah. For more distant galaxies where we can't see individual stars that clearly, we use a different trick. We measure the average speed of stars in the central bulge of the galaxy, the velocity dispersion. There's a tight relationship between that dispersion and the mass of the central black hole.
Okay, stellar mass, supermassive. But you mentioned 3 classes. What's in the middle?
Ah, yes. The elusive intermediate mass black holes, or IMBHs, these are the ones hypothesized to fill that gap, maybe from 100 up to, say, 10,000 or even 100,000 solar masses.
Hypothesized, so we're not totally sure about these.
They're much harder to find and confirm. They're kind of gravitationally awkward. Too heavy to be from a single normal star's collapse today. Too light to be the supermassive seeds we see in galaxy centers.
So where are people looking for them?
Dense environments are the best bet. Places like the cores of massive globular clusters, those ancient, tightly packed balls of stars. There's a famous candidate in the globular cluster G1, which orbits the Andromeda Galaxy. Estimates put a dark object there at around 20,000 solar masses, right in the IMBH zone.
Okay, if they don't form like the stellar ones, how might these IMBHs actually come about? What are the theories?
Well, there are a couple of leading ideas based on the sources. One possibility goes way back to the early universe. The very first stars, population 3 stars, were made of just hydrogen and helium. no metals.
Right, metal poor.
Exactly. And without metals, they didn't have those strong winds we talked about. So they could have grown enormous, maybe up to thousands, even 10,000 solar masses, and then collapsed directly into IMBHs.
A direct collapse of a primordial giant.
That's one path. Another idea is more dynamic. It involves runaway collisions in really young, really dense star clusters. Imagine stars merging over and over again, building up a central massive object that way. It could potentially gobble up enough mass to reach maybe like 0.1% of the whole cluster's mass, forming an IMBH.
Okay, so we have the different sizes and some ideas on how they form. Now, the power source. How do these things become the brightest objects in the universe? You mentioned feeding accretion.
Accretion, yeah. It's all about gravity converting potential energy into radiation as matter falls in. And the efficiency is just stunning.
More efficient than nuclear fusion, right?
Oh, vastly more efficient. Think about the sun, burning hydrogen to helium. That's fusion. Its efficiency, converting mass to energy, is about 0.7%, less than 1%.
Okay.
Now, take matter falling onto a compact object like a neutron star or a black hole. The process of accretion, just the spiraling in and heating up due to gravity and friction, can release energy with up to, say, 20% efficiency, maybe even more for spinning black holes.
20% compared to 0.7.
Yeah, it's like 30 times more efficient. That's the key takeaway. When it comes to raw power generation from matter, gravity crushes nuclear energy, especially around black holes.
That incredible power must create some feedback, right? Like, can a black hole feed too fast? Is there a limit?
There is a theoretical limit called the Eddington limit. That's the point where the outward push from the light generated by the accretion, the radiation pressure acting on electrons in the gas, exactly balances the inward pull of gravity.
So if you try to feed it faster than that, the light should just blow the incoming fuel away.
That's the standard picture, yes. But black holes have a trick up their sleeve, especially compared to neutron stars. They can actually sustain accretion rates much higher than the Eddington limit.
How? How do they beat their own radiation pressure?
Through a process called advection. Basically, when the gas is flowing in really, really fast and gets incredibly hot right near the event horizon.
The point of no return?
Right. The photons generated in that super hot gas don't really have time to escape outwards and push back effectively. They get dragged or advected inwards along with the gas flow and swallowed by the black hole.
So the black hole literally eats its own light pressure.
In a manner of speaking, yes. It allows the feeding frenzy to continue even when it technically should have choked itself off. It's a crucial feature for understanding the brightest quasars.
That's mind-bending. Okay, so the environment near the horizon is key. This brings us to the black hole itself, and you mentioned spin. How important is the black hole's rotation?
It's fundamentally important. A spinning black hole isn't described by the simple Schwarzschild solution, but by the Kerr metric. And that spin is quantified by this dimensionless parameter, Day-Geller, which goes from 0 for no spin up to 1 for maximum spin.
And what does the spin change?
It dramatically alters the space-time geometry right near the hole. One of the most critical effects is on the location of the innermost stable circular orbit, the Risco.
A stable place to orbit.
Exactly. It's the point inside which matter can no longer maintain a stable orbit. It's doomed to plunge in. For a non-spinning black hole, Risco is relatively far out, at 6 times the gravitational radius. But for a maximally spinning Kerr hole, Risco shrinks dramatically, getting incredibly close to the event horizon itself, down to about 1.2 times the gravitational radius.
So spinning it up lets matter get much closer before falling in.
Precisely. And getting closer means falling through a deeper gravitational potential well, which releases significantly more energy just before that final plunge. Spin boosts the accretion efficiency even further.
Okay, mass, accretion rate, spin. But you started by saying the viewing angle was also critical. How does where we stand affect what we see? You called it unification by angle.
Yes, this was a huge realization, especially for active galactic nuclei, the supermassive ones. We used to classify them into all these different types based on their spectra, like Seyfert-1 and Seyfert-2 galaxies. They looked fundamentally different.
Seyfert-1s show broad emission lines. Seyfert-2s only narrow lines, right?
Correct. The unification model explains this beautifully. It proposes that they are intrinsically the same kind of object. A supermassive black hole accreting matter, surrounded by a thick, dusty torus, or donut, of cooler material. If we happen to view the system from above or below the torus, face on, we get a clear view of the hot, fast-moving gas near the black hole, the broadline region, or BLR. That's a Seyfert-1.
Okay, direct view.
But if our line of sight is edge-on, through the plane of that dusty torus?
The torus blocks the central region.
Exactly. The torus completely obscures the BLR. We only see the narrower emission lines from gas further out. That's a Seifert 2. It's the same engine, just seen from a different perspective. The viewing angle unifies the zoo.
That's elegant. Does the same idea apply to the smaller stellar mass systems, the microquasars?
Absolutely. A classic example is the microquasar GRS 1915 plus 105. It's famous for launching these incredibly powerful relativistic jets.
Jets moving near the speed of light.
Very near. And when one of these jets happens to be pointed almost directly at us, the viewing angle is very small. Then relativistic effects like Doppler boosting and time dilation create an illusion.
An illusion? What kind?
The blobs of plasma in the jet appear to be moving faster than the speed of light. We call it superluminal motion.
Whoa, hang on. Faster than light? I thought that wasn't possible.
It's not actually faster than light. It's an apparent speed caused by the geometry and the fact that the source itself is moving towards us at nearly light speed while emitting the light we see later. We've measured apparent speeds in GRS 1915 plus 105 up to maybe twice the speed of light, sim 2 tall. It's wild, but it's perfectly explained by Einstein's relativity. And it tells us the jet's true speed is very high, with the Lorentz factor around 5.
So the superluminal motion is actually proof of relativity and confirmation that these microquasars are behaving just like the giant quasars, just scaled down.
Precisely. It reinforces that unification idea. The core physics is the same.
Okay, let's talk more about those jets. They're like the exhaust system of the black hole engine. How are they actually launched? What gets them going?
The leading theory involves magnetic fields anchored in the accretion disk spinning around the black hole. It's often called the Blandford-Payne mechanism, a magnetocentrifugal process.
Magnetocentrifugal, like a magnetic slingshot.
Sort of, yeah.
Oh.
If the magnetic field lines threading the disk are tilted outwards, away from the rotation axis by more than about 30 degrees, then as the disk rotates, the magnetic field acts like beads on a wire. It flings the plasma outwards and upwards, accelerating it into a focused jet. The magnetic field provides the channel and the initial push.
And what are these jets made of, especially right near the black hole? Is it just hot gas, plasma?
Very close in, especially if the jet is powered directly by the black hole's spin energy, which is the Blandford-Znajek process, extracting energy from the ergosphere.
The region where spacetime itself is dragged around.
That's the one. Outflows launched from there are thought to be initially dominated by magnetic energy, not the kinetic energy of particles. We call it a Poynting flux-dominated outflow.
So more like pure electromagnetic energy than a stream of matter.
At the very base, yes. It's thought to be highly magnetized, maybe even electron-positron pairs initially. Further out, it might pick up heavier particles, but the magnetic field likely plays the dominant role in collimating it and carrying the power over vast distances.
Incredible. Okay, beyond jets, there are even more violent events linked to black holes. The sources talk about gravitational waves and gamma ray bursts. Let's touch on GWs first.
Right, gravitational waves. Ripples in the fabric of space-time itself, predicted by Einstein a century ago, and now something we can directly detect. They are generated by the most extreme gravitational events.
Like black holes merging.
Exactly. Especially binary systems of compact objects, 2 black holes, 2 neutron stars, or a black hole and a neutron star spiraling into each other. As they orbit closer and faster, they radiate gravitational waves, losing energy.
And the signal has distinct phases, right?
Yes, typically 3 main phases we look for in the data from detectors like LIGO and Virgo. First, the in-spiral, where the 2 objects orbit each other, gradually getting closer and faster, emitting a chirp signal that increases in frequency and amplitude.
Okay.
Second, the merger itself. This is the most violent part, where the 2 objects collide and coalesce into a single, larger object. The space-time distortion is maximal here.
And finally?
The ring down. The newly formed single object is initially distorted, kind of wobbling. It settles down into its final stable state, usually a curved black hole, by radiating away the last bit of energy as gravitational waves, like a bell ringing down.
A cosmic symphony of merging black holes.
Mm-mm.
Okay. And the other cataclysmic event?
Gamma ray bursts.
Gamma ray bursts, or GRBs. These are arguably the most luminous electromagnetic events we know of since the Big Bang itself. They release truly colossal amounts of energy in gamma ray.
How luminous are we talking? We measure their brightness, assuming they radiate equally in all directions, the isotropic equivalent luminosity. And that can reach up to something like $3 times 10 ergs per second. It's so much energy that when they were first being studied intensely, people talked about an energy crisis. How could anything produce that much power?
Where are they come from? Are they in our galaxy?
No, they are cosmological. We see them from billions of light years away across vast stretches of the universe, and they seem to fall into two main groups based on how long the burst lasts.
Yes, the short versus long duration bursts.
Exactly. Long-duration GRBs, LGRBs, last longer than about 2 seconds. The evidence now overwhelmingly links these to the core collapse of very massive, rapidly rotating stars, likely stripped of their outer hydrogen envelopes. It's often called the collapsor model, essentially a specific rare type of supernova that forms a black hole and launches jets.
Okay, so LGRBs are from collapsing massive stars. What about the short ones?
Short-duration GRBs, SGRBs, last less than 2 seconds, sometimes just milliseconds. These are strongly linked to the merger of two compact objects. Usually it's thought to be either two neutron stars, NS plus NS, or a neutron star merging with a black hole, NS plus BH. The gravitational waves from such mergers are often detected alongside the GRB signal now.
So we've gone from the different types and sizes through how they feed and generate power via accretion, spin, and relativity, and finally to their outputs, the jets, the gravitational waves from mergers, and the gamma ray bursts from collapse or mergers. It's quite a picture.
It really is. And the amazing thing looking back at all the sources is how coherent it becomes. The physics, grounded in general relativity and magnetohydrodynamics, seems to describe all these phenomena across all these mass scales.
So the takeaway is predictability, despite the chaos.
I'd say so, yes. It seems like black hole systems are highly predictable if you know those few initial conditions. The mass, the spin, and the accretion rate. The incredible variety we observe often boils down to just how much fuel is available and, crucially, that viewing angle we talked about.
It's amazing how viewing angle plays such a huge role. Now, you brought up something quite sobering related to GRBs, the potential threat to life on Earth.
Yeah, it's a connection that grounds this extreme astrophysics. A sufficiently powerful GRB, if its jet were aimed directly at Earth and it happened close enough within maybe a few hundred parsecs, which is still pretty far,
It could be bad news.
it could potentially trigger mass extinction events, maybe by damaging the ozone layer severely. It's a real, though likely very rare, cosmic hazard. Makes you think about our place in the universe.
But the sources mentioned a kind of cosmic stay of execution, some recent findings that might mitigate this threat.
That's right. It's quite fascinating. Recent studies strongly suggest that the most powerful type of LGRBs, the ones from collapsing stars that pose the biggest threat, don't happen randomly everywhere. They seem to occur preferentially in smaller galaxies, often irregular ones, that have low metallicity, meaning they haven't had many generations of stars to build up heavy elements yet.
Not in big spiral galaxies like our Milky Way.
They seem to be much rarer here, yeah. Our galaxy is relatively metal-rich. If this preference holds true, it means the odds of a truly devastating GRB happening close enough and aimed at us are significantly lower than previously thought. It might push the average time between such lethal events in a galaxy like ours out to maybe 5 or 10 billion years or even longer.
So while the gun is loaded, it seems less likely to be pointing at us, or at least less likely to fire nearby. A cosmic stay of execution, indeed.
It offers a bit of cosmic reassurance based on understanding the environments where these extreme events are born.
That's a fantastic point to end on. We started trying to unify the physics of black holes across all scales, and we end up realizing that the specific conditions of their birth might just be what allows life like ours to persist. It brings it all back home.
It does, doesn't it? Pleasure discussing it.
And for you listening, we hope this deep dive encourages you to keep exploring the absolute wild, interconnected universe of black hole physics. We'll catch you on the next one.